Hello everyone, it's me, Mr. Younger again, and I'm going to show you another example of how to calculate torque. In this case, it's actually a three-dimensional drawing where I have laid enough dashed lines for you to make out the coordinates of points, the changing coordinates from one point to another, and so on and so forth. And you're going to be asked to create the actual vectors for the lever arm and for the force, given the magnitude of the force and just given the diagram for everything else. So I'm going to use the determinant method, basically expanding along the I hat, J hat, and K hat terms, but I also do other methods in later examples. So let's go ahead and get started by sharing my iPad screen with you guys. So you can see that in this problem it says the green box has a force F, which I listed as having a magnitude of 50.0 newtons, acting on it at the point 1 meter, comma 2 meters, comma 4 meters. Assuming the coordinate origin is the pivot point, find the lever arm vector and the force vector in IJK notation and compute the torque on the box. So that's what we're trying to do here. I am going to go ahead and write out our solution as follows. Since I'm asked to find these vectors in IJK notation, it seems obvious that they're wanting us to actually compute the torque using the cross product. So I'm going to say torque is equal to R, the lever arm vector, crossed with F, the force vector. And I want to remind you that the force vector is technically not a vector whose components are in meters. It's not positions and so on and so forth. But you can put it in such a coordinate system like I've done here and draw geometrically how it fits. And then you have to assume that it's what you call a similar vector, in that it's the exact same scale ratio. Like if you took the z component divided by the y component in the space in meters, you would get the exact same thing if you did it in newtons with the x or z component divided by the y component, and the same thing with the z component divided by the x component, and the same thing with the x component divided by the y component. So in that sense, we can use the geometry of these points from the tail end of the vector to the head end of the vector to figure out basically how the or a line in space that the vector is parallel to. Once you have that line in space, in principle, you can make it a unit vector and then just multiply it by the magnitude, and you would achieve exactly the vector you want. Additionally, the lever arm vector is supposed to be the vector from the origin to the little point that I labeled with that fancy P, i.e. the point 1.00 meters, comma 2.00 meters, comma 4.00 meters. So we're going to go ahead and try that. I will remind you that torque is given by a determinant according to this. So we could say torque is equal to the determinant. This time I'm actually writing the determinant notation, so I'll actually take time to write the vector, or excuse me, the matrix as a curved a curved matrix boundary, basically. So I'm going to put I hat in the first row, first column, J hat in the first row, second column, and K hat in the third row, third column, or excuse me, in the first row, third column. Now I'm also going to put in my R sub x, my r sub y, and my r sub z, and my f sub x, f sub y, and f sub z. What we do with this, remember, is I expand on each of the terms. So what I'm going to do is I'm going to write I hat first. And of course, when I'm expanding upon I hat, that eliminates this row and this column, leaving just this vector down here. And I'm supposed to multiply it by -1 to the I plus j power, where I is the row and j is the column numbers for the I hat. So since we're expanding on I hat is in the first row, first column, so we're really multiplying it by -1 raised to the 1 plus 1 power. That's 1 for the row, 1 for the column, 1 plus 1 gives you 2, -1 to the 2 power gives you 1. So it's just I hat times the remaining vector, the remaining matrix determinant. And as I showed you, once we've chosen I, that eliminates that row in this column, and we're just left with this vector. So the determinant should be this times this minus this times this. So again, writing that down, and I'm actually giving you a general formula that, as you'll see on the spreadsheet as well. This one has to be ry times fz minus rz times fy, then plus j hat. Now j hat is this one right here, so that means we're going to eliminate this column and this row. It also means that it's in the first row and the second column. So that 1 and 2 are our I and J that we add together. That 1 and 2, when we add them together, is 3, and then we raise -1 to that power. That is -1 to the third power. It gives you -1 times -1 times -1, which is -1. So this one you're actually supposed to multiply by -1. I normally don't do it that way. I normally just do the determinant backwards. So in general, when you're expanding on J, again, that means this row and this column is eliminated. So you basically have a matrix made of this column and this column. And normally our determinant would be Rx times Fz minus Rz times Fx, but because of the negative that pops up for the J, I'm going to do it as Rz times Fx minus Rx times Fz. And that's my J hat term. And then finally, we have a K hat term. Now, K hat, of course, has the or is in the first row and third column. So the I and J are 1 and 3. If you add 1 and 3, you get 4. -1 to the fourth power is -1 times -1, which is 1, times -1, which is -1, times -1 again, which is +1 again. So we just take the normal determinant of this matrix in the technique that I use. But again, we do have to, since we're taking K and expanding on it, we have to eliminate this column and this row. So that just leaves us this matrix. And since there's no negative, we're just going to do it in the typical order. So in this case, we're going to get RxFy minus RyFx. And that's the formula via determinants. So as soon as we figure out what the vector r is or what the vector f is, we can just blindly use this formula. We don't even have to think about the matrix. You can just write this formula down from your from your equation sheet and use it. But I'll also show you other ways. So for starters, what I see when I look at the lever arm vector, the lever arm vector is the vector that goes from the pivot point to the point of application of force. We said the pivot point is going to be the origin. So that suggests that we should actually have a lever arm vector that goes from the origin to that point right there. So that's our lever arm vector. You can see that in order to get to that point, I could go from the origin, which is where the starting is. I could go 1 meter in the positive x direction, and then I could go 2 meters in the positive y direction, and then I could go 4 meters in the positive z direction. That tells us, since this is a vector in space, unlike the force vector, that tells us exactly the components. In fact, a way of calculating a vector in any space is you take the coordinates of the head of the vector and subtract from it the coordinates of the tail of the vector in order, so that you take, for instance, the x value of the point in the head minus the x value of the point where the tail is, the y value at the point of the head minus the y value at the tail, and the z value at the point of the head minus the z value at the point of the tail. That is the a way to immediately get a vector that's plotted in space, and you want it to have components that are space-like, i.e., have units of length as their components. So with that in mind, I'm going to go ahead and use what I found. The r vector, in fact, has, as I showed you here, we're going to go from the origin, which is the pivot point, I'm going to go forward 1.00 meters in the positive x direction. I'm going to hang a right and go 2.00 meters in the positive y direction. And then I'm going to go positive 4 meters in the z direction. So that means our vector is 1.00 meters times I hat plus 2.00 meters times j hat plus 4.00 meters k hat. So that's our vector, one of the vectors they're wanting. So I'm just going to underline it so we can easily pick it out. Now I've also got to figure out the vector. So a similar vector to f is found as follows. So what I'm saying is a similar vector to f. This is a vector in space that I'm talking about now. Uh, that similar vector in space will be exactly parallel to this vector in, force space if you wanted to make it. The main thing is I'm saying that really a vector of force has a unit of force that is in Newton or has a components that are in newtons. So Newton, some number of newtons times I hat, some number of newtons times J hat, some number of newtons times K hat. In this case, we're actually using them to start off as just coordinate points. So if we look at this vector, it appears that if we start at the tail, we would have to go down 1 unit in the y direction. We have to go forward in the positive x direction by exactly 1 meter, and then we have to go in the negative x direction by exactly 2.00 meters. Excuse me, no, not two. That's one, two, three, four, five. That's 5 meters to the left because the way I've got this set up is I'm actually using these rectangles or the squares on my graph paper as whole units. So I can say, let's call this vector tilde f because it's not really a force vector. And it is a vector, so I'll put a symbol over it. So what I'm going to say is clearly the x component is negative, and it seems to be negative again. One, two, three, four, five. So I'm going to say it's negative 5.00 meters times I hat plus, in this case, it did go from here to here. Oops. The y component, or that was the x component. My fault. I was doing the y component as the 5. Sorry about that. Let's fix this real quick. I said it right, but I was literally just writing it in the wrong slide. So, uh, if we take this part of the vector first, then that would be the x component, but I mistakenly took that part. I don't know why I even started there, but anyways, we're going to go ahead and take this part, which is the x component, and you can see it's in the positive x direction. So it's positive, and in fact, it's the same length as this, which is 1 meter. So this one's going to be positive 1.00 meters in the I hat direction. We're also going to do in the y direction, which the y direction goes from here to here, and that does seem to be the negative y direction, and it does seem to be 5 units. Again, you can tell that by basically looking at the fact that this is 1 meter and this is 2 meters by default. Since this is 2 meters, half has to be 1 meter. So this must be 3 meters, 4 meters, 5 meters, 6 meters, 7 meters. So 7 meters is where this end is lined up at, but this end is already lined up at 2 meters. That's where I get the 7. So I'm going to put plus negative 5.00 meters. I think I just said that's where I get the 7. Uh, that's actually where I get the 5 because it is 7 all the way to here, which is also here. That's 7 away from the XZ plane. But this side right here is 2 away from the XZ plane. So this distance from here to here is just 7 minus 2, which is 5. So that's why I got 5 meters, negative 5 meters, j hat. Oops. And then the k hat direction, you can see that I clearly just went down by 1 unit. Uh, Again, you can look at that and see uh, that that would just be 1 unit because right here there's 1 unit, 2 units, 3 units, 4 units. So obviously the vertical squares are 1 unit long and 1 unit being 1 meter. So now I can say plus negative 1.00 meters k hat. What I want to do is find the magnitude of that vector specifically because once you find the magnitude of a vector, you can divide that magnitude by or into the vector itself, and that'll give you a unit vector. And it's purely a unit vector. It has no units. In other words, you're dividing by the magnitude, which will be in meters, and the components are in meters. So when you divide them meters by meters, you get no units. You just get a pure number. Then all we have to do is take that pure vector that has no units and multiply it by 50.0 newtons, and that'll give us the force vector. So this is just a typical thing you're exposed to be able to do in terms of algebraic processes with vectors. So let me show you how that's done. Now, it does turn out that the Pythagorean theorem is true in 3 dimensions too, so it's not just x squared plus y squared is equal to the hypotenuse squared. You could also say x squared plus y squared plus z squared. Square root of that is equal to the magnitude. So we can do that as well. So what I'm going to do is find the magnitude of f tilde, and that would be 1.00 meters squared plus negative 5.00 meters squared plus negative 1.00 meters squared. Take the square root of all that, and we're going to get 1 plus 25 plus 1. That would be the square root of 27, and 27 doesn't really make things any nicer, but I can say specifically that the square root of 27 is 3 root 3. Oops, sorry about that. Is 3 times the square root of 3, but that also is equal to, in decimals, approximately 5.19. That's the 3 sig figs we already had. I'm going to add 2 more like I normally do, so I'm going to say 6 and then 2 meters. So that's the actual magnitude of F tilde. Now, if I divide F tilde by the magnitude of F tilde, then I get a unit vector that points in exactly the same direction as the purple vector, which is what we want. So when I do this, all I have to do is say F vector unit. Well, actually, let's put a hat over it because that's what we use when we're wanting to indicate a vector is a unit vector. That vector is going to be uh, 1 over 3 root 3 I hat minus the next component was 5.00 over 3 root 3 j hat, and then the next one was minus 1 over 3 root 3 k hat. So we can actually get those individual components as, numbers without square roots as actual decimal places. So for instance, 1 divided by the square root of 3, or excuse me, 1 divided by parentheses 3 times the square root of 3, close parentheses, uh, did something bad on my calculator here. Oh, there it was. Okay, so 1 divided by 3 square root of 3 is 0.19245. Now, that 4 and 5 are not significant, so I'm going to call that the I hat component. Also see that if I multiply that by 5 and negative 1, I get the y component, so it's going to be negative 0.96225 j hat, and then of course the z component is the same as the x component, only it's negative. So I'm going to say minus 0.19245 k hat. So that is a unit vector, and just to check, you would probably want to take a square of each of those terms and add them and take the square root. You shouldn't even have to take the square root. It should come out to be exactly 1. So just trying that, I'm typing in 0.194 or 245 squared plus 0.96225 squared plus 0.19245 squared, and that gives me 0.99999900675. So that's really, really very close to 1. So now finally I can say the actual force vector is equal to 50.0 newtons times f hat, and of course that's always true. Anytime you find a unit vector, you can multiply it by the magnitude you want, and that'll automatically give you the vector that you want. So with that in mind, this is going to be 50 over root 3 over 3. I hat minus uh, 50 times 5 is 250 over 3 square root 3, and that's j hat, and then minus 50.0 over 3 root 3 k hat, and this is the vector in newtons. So all we have to do now is compute the matrix, or compute the cross product of these two. I'm going to go ahead and underline this vector as well, so we'll know, essentially at least know which vector is which. So this is the vector we're using in addition to the one we drew up there. So we should go ahead and get started with that using our new determinant formula. So I can go ahead and compute RYFZ minus RZFY if I wanted to. And what I'm going to say is torque in this case. I'm trying to get my color back. I'm going to say the torque in this case is actually equal to I hat times, now I'm going to take RY times FZ. Well, RY is just 2, and then I multiply it by FZ. That is 2 times negative 50 over 3 root 3. So that is negative 100 over 3 root 3. And that's just RY times FZ. Now I got to do minus RZ times FY. So if I take RZ, which is 4, and multiply it by FY, which is 5, negative 5 over 3 root 3, I'm going to multiply 5 times 4, and that's going to give me negative 20. 5 times 4, yes, negative 20 over 3 root 3. And that's the first term. The second term is the j hat term, and we found that was RZFX minus RXFZ. So RZ is 4 and fx is 50 over root 3. 4 times 50 is 200. So this is going to be 200 over 3 root 3 because again, I'm just multiplying RZ, which was 4, times 50 over root 3 over, excuse me, I'm multiplying RZ, which is 4, over 50 times 50 times over this 3 times the square root of 3. Ooh, that was hard to say. Okay, so now I've got that. But the other part of it is Rx minus Fz, so I have to do minus. Now I want to take Rx, which is 1, and multiply it by Fz, which is negative 50. So this is going to be negative 50 over 3 root 3, and that's my j hat term. Now I'm going to add my k hat term, and my k hat term is going to be Rx minus Ryfx. Well, Rx is 1 and Fy is 250 times the square root of 3. And now I'm thinking I might have made a mistake earlier when I was doing my numbers. So I'm going to check that back again. But Rx, again, like I said, is 1.00 meters and Fy is negative 250 over 3 root 3. So this should be negative 250 over 3 root 3. Again, that's supposed to be Rx times Fy, so that's 1 times negative 250. Now I got to do minus Ryfx, so Ry is 2 and Fx is 50. So this will be minus 100 because 2 times 50 is 100 over 3 root 3. So let me double check these other ones. I'm looking at the I hat component again. The I hat was supposed to be Ry times Fz. Maybe I'll write this in the bottom. Ry times Fz should have been 2 times Fz, which would have been 50 over 3 root 3 minus, now in this case it's RZFY, and RZ is 4 and Fy is negative 250. So yeah, this should have been 4 times negative 250 should have been negative 1000 over 3 root 3. I don't know how I ended up getting 20 instead of 1,000, but I sensed I did that because I remember not using the 250 yet. I think I might have looked at the vector above it by accident or something. Now that we have that, we can go ahead and see that I have one mistake. I'm going to go ahead and fix it, but I want to double check, make sure I did what's right. So again, we're taking Ry times Fz. Ry was 2 meters, and then Fz was 50 over negative 50 over square root of 3. So that works. And then I took RZFY. RZ, of course, was 4. And then 4 times Fy. Fy was negative 250. So that'd be negative 1000. So I double check that. Now that means this number is going to become negative 1000 here. Oops. Technically, neither of those are sig figs. And all of this, of course, is coming out in Newton meters. So I checked that one. Now let's check J. That's supposed to be RZFX. Well, RZ was 4. So writing this down here, we should get 4 times FX. And FX is the 50 over 3 root 3. And then we're supposed to subtract from that Rx times Fz. So Rx we know was 1 times Fz we know was negative 50 over 3 root 3. And that should give me 200 minus 50. Yep, minus minus, that gives you plus. Yep, that works. And just double checking on the last one, even though I was more careful there, Rx was in fact 1. Whoa, no. Rx was in fact 1, and then Fy was in fact negative 250 over 3 root 3, and then minus, but in this case it's Ry minus Fz. Ry is 2, and Fz is negative 50 over 3 root 3. So we should actually have a double negative there. So I did make a mistake on that one as well. So just I'm glad we went back over this. Now we can ultimately just figure out what the results are. But to do so, it would be really helpful to have more room. So I'm going to steal this by copying it over to the next page. Copy, paste. So that's the actual result we have. Obviously, I could erase that red line and stuff like that, but it's not really relevant. I'm going to go ahead and say now that the torque is, obviously everything has 1 over 3 times the square root of 3 in it. So I just pull that out in front. And what I'm getting is negative 100 minus negative 1,000. So that's 1,000 minus 100. So that's 900. 0.0 newtons times meters times I hat. And now the next one is 200 minus negative, which would be adding. So 200 plus 50, that would be a positive 250.0 Newton meters for that one, and that's J hat. And then finally, the last term, I get negative 250 minus negative 100, so that's 100 minus 250, which is negative 150 Newton meters again, and this time it's times K hat. And now I can close the curly brackets. And finally, I can get that the torque is, I could leave it in terms of 3 root 3, but that's not very physically meaningful. So I'm going to take the 900 and divide it by 3 times the square root of 3. Actually, I'll just divide it by square root of 27. It'll be easier. So I'm going to say 900 divided by 27 to the 0.5 power gives me 173.21 Newton meters I hat. 250 divided by 27 raised to the 0.5 power gives me 48.113 Newton meters J hat. And then finally, the last term, I'm going to get 150 divided by the square root of 27, and that's going to give me 28.868 Newton meters K hat. So that is actually the net torque. That is another way of doing it, other than the way that I showed you on example 1. This is just blindly plugging the formula in. Of course, there's other ways as well, but I think this is a good exercise so you guys can figure out how to implement the cross product in such a way that it's not so time consuming. You can just apply a formula, but you see it has a lot of potential errors coming in it because it's a little bit tedious. There's a lot of little details. So hopefully that helps you better understand how to do the torque calculation, as well as I'm hoping it taught you all a lot about how you can manipulate vectors and make vectors just by seeing diagrams and stuff of that sort. So hope that helps you and have a nice day.